So today I'm going to talk to you about verifying object construction, or how to get the type safety of constructors with the flexibility and readable client code of builders. So why would people like a constructor? So suppose we have a class like user identity as it's shown on the screen with a name and an ID and a nickname. And the name and ID are required, nickname is optional. Typically, we would write constructors like these, a user identity constructor that takes the two required parameters, and then one that takes the required parameters and the optional parameter. So let's suppose that for some reason, we're going to try to create a malformed user identity, one without an ID. So we might call new user identity of my name. And of course, if you're a Java programmer, you know that this will fail. Right? This is totally rejected by the Java compiler because there's no such constructor. And so that's the great thing about constructors. You get compile time verification that the arguments are sensible, or that the required arguments are provided. Because you just wouldn't write a constructor that didn't have all the required arguments. Like, why would you do that? But the constructors do have some downsides. So the user has to write each of them by hand. There are exponentially many in the number of optional parameters. We saw that there were 2 when we had just 1 optional parameter. We had 2 optional parameters. We need each combination and so on. And the arguments are positional, so it can be hard to read client code. So to deal with these issues, programmers sometimes use other object construction APIs, like the builder pattern. It's a classic design pattern. And in the builder pattern, we have a separate builder object that has setter methods, like a name setter, an ID setter, a nickname setter, and so on. And a build method at the end. And the build method actually constructs the target object, the object we actually want. And this leads to neat client code like this. Right? We call it user identity at builder, we call name, we call ID, and so on. And this is much more readable client code. So this is why programmers like the builder pattern. The client code is flexible and easy to read, and a framework will implement all that boilerplate I showed you on the previous slide, or on an earlier slide, automatically. But what would happen if we tried to make the same mistake that I showed earlier, that the compiler caught when we were using constructors, that is, omit the ID parameter? Well, the compiler here is actually going to accept this, because the compiler doesn't know that this is not supposed to happen. And so what does happen instead? In the best case, we'll get a runtime error. Like when we try to actually call build, there might be a null check, for instance, inserted in the builder's build method for a required parameter. So lots of frameworks will support this. But this is still a crash, right? We failed at runtime, and this is still undesirable compared to catching the problem at compile time. But in the worst case, there's no such check. And we call build, and all appears to be well. But later on down the line, the fact that there's no ID causes some other problem. And in the worst, most serious cases, including some that we'll evaluate on later, this can cause like a security vulnerability because of some missing information. So that shows us the big downside of the builder pattern. There's no guarantee that the required arguments are provided, no compile time guarantee. And this is one of the most requested features for these builder pattern generation libraries. So on the screen are some examples from Lombok, which is one of the builder generation libraries for Java. And in a blog post, the leader of the Lombok project said that they get this feature request, that is compile time detection of required parameters, every other week. And so the highline result here is that with the approach that I'm about to describe, we can provide type safety for uses of the builder pattern. We can get all the safety of constructors, but retain the same code that we use for, same client code that we use for the builder pattern. That is, we'll retain all the advantages of the builder pattern. Now I want to just give you a high-level idea of the core of how we do this. So I want you to consider the builder example on the left, same one from before, and I want to consider encoding this as a type state analysis. In that case, what we're going to do is we're going to construct a finite state machine for a builder object, and then we're going to transition the finite state machine as we analyze the program. So at the start, we're going to assume that nothing has been called on the builder, and when name is called, we transition into a name-only state. When ID is called, we transition into a good state, once both have been called, where we're allowed to call build. And then if we call build earlier, then we transition into a failing state that we can't get out of. And the analysis issues an error if we ever discover that any of the builders in the program are in the failing state. And this is a totally sound approach, right? This is going to work. But the problem is that type state analysis in general is extremely expensive. And so it's not feasible for a programmer to, say, run it on every time that they compile their code. It's just too expensive. And the reason is that it needs a whole program alias analysis in general. An alias analysis or pointer analysis, meaning that all the finite state machines for the same object for all of its aliases have to be in the same state all the time. But what we've noticed here is that for these builder-derived finite state machines, they have a key property that is going to allow us to dispense with this alias analysis. And that's that transitions flow only in one direction. That is, there's no transition that takes us out of this build state. So once we're into this state where we can build, we can't get back out of it. And this leads us to the idea that we can devise a special case here, right? And in fact, we do have such a special case. We call it an accumulation analysis. So a finite state machine like this fits into this idea of an accumulation analysis where the transitions only flow in one direction. And once you reach this accepting state, you can't get out. And an accumulation analysis has some really nice properties. First, it's always safe to under approximate. Right? We can always forget information, right? And still retain soundness. And this means that we can dispense with the alias analysis. So we don't have to keep the finite state machines for aliases in the same state as long as we always choose a conservative under approximation. And that allows us to implement this modularly, right, as a type system, a standard type system, layering on top of the host language. As a type system, we get some neat advantages. Right? We still get the same kind of soundness guarantees as the full type state analysis. But we don't have to run a full alias analysis, and we can be modular, which means that we are much more scalable. We can run on huge amounts of code much more quickly than a standard type state analysis. And then we can use all the standard tricks from the type system book to reduce the need for human written annotations and so on. So in the end, we end up with a specification for the builder that looks like this. So we have an @called methods annotation. This is the type. And the called methods annotation says that name and ID have to be called before build. And we built such a tool, and then we ran it on in a number of cases, right? And I just want to highlight one, which is a case, like I mentioned before, where there's a security vulnerability if one of the arguments to a builder isn't provided. So we ran on about 9 million lines of code, and in those 9 million lines of Java code, we found 16 such vulnerable requests, or 16 such vulnerable builders with only 3 false positive warnings. So we issued 19 warnings, 16 of them were true vulnerabilities, and we only needed 34 human written annotations in all that code to get it to verify. So that's it. We're able to produce the static safety of constructors with the flexibility of builders using this technique and using this accumulation analysis technique, which is a special case of type state that does not require a whole program alias analysis. Our tool is publicly available, and I'd be happy to take any questions that you have.